Dear ladies and gentlemen, dear colleagues, my name is Andjelka Kovacevic and I am a member of LIFE team. Lead of the project office and part of the science team is Daniel Angerhausen from ETH Zurich. It's a great honor to be here to see excellent works of various researchers and research groups. We thank you to organizers of 6th NorCell Conference for giving us the opportunity to present this report on early prototypes of statistical experiments related to the question whether survey of habitable planets in the solar neighborhood can be used to distinguish between models for the origin of life. Detecting and characterizing terrestrial and temperate extrasolar planets in the solar neighborhood will be a major scientific frontier in upcoming decades. Current observational facilities provide first glimpse into the vast variety of potential habitable planets. Existing or soon to be operating space telescopes such as LIFE will have the capabilities to characterize small sample of those individually. In the next step, comprehensive and systematic survey of the atmosphere composition of these rocky planets with temperatures right for liquid surface water will enable us to answer questions also on the population level. We will put our question whether systematical survey of habitable planets in the solar neighborhood can be used to distinguish between the models for the origin of life in the context of the nearby Future Space Survey LIFE mission. And we will present early 2 ongoing prototypes of experiments we are performing in the preparations. LIFE is an ambitious space mission with unparalleled scientific capabilities optimized for the direct detection and atmospheric characterizations of hundreds of exoplanets, dozens of which will be terrestrial, temperate, and possibly hospitable to life as we know it. As a formation of flying mid-infrared nulling interferometer, LIFE will be located in Lagrangian 2 point and consists of 4 collector spacecraft with 2 to 3.5 meters apertures and a combiner on the right spacecraft. Observing wavelength range will be between 4 to 17.5 micrometers with the goal to wider this range between 3 and 20 micrometers and with required spectral resolution about 35 with the goal of 50. Total emission lifespan is 5 to 6 years. The search phase lasting for 2.5 years will be focused on detection of hundreds of planets, and the next session of 3.5 years will be dedicated to characterization phase with detailed investigation of atmospheric diversity and search for biosignatures. Other science will be dedicated about 20% of the LIFE mission time. In general, the model and corresponding parameters describing life emergence, even in our solar system, are completely unknown. There are 2 major hypotheses of life emergence: abiogenesis and transmission. Former is investigated within astrobiology as a poisson process, while the later assumes pandemia-like diffusion models. Fortunately, there is a possibility to express diffusion model as a Poisson process, and such expression could give mission. The goal here is actually to make some strategies that are most likely to delineate somehow between these 2 models. Taking into account that there are several types of numerical experiments, what we anticipate to get with LIFE mission maybe 2 dozens of habitable exoplanets. For some, we might find life. For some, we will find no any trace of life. And for some, we would never know anything about it. And we are coming to the first prototype statistical experiments. That is the early, very early stage, and we need advice from experts like you. In any epidemic, parameter R is actually measure known as the effective reproduction number. It is the number of infected per infectious person and time. When this number is larger than 1, the pandemic will affect large population, while when this number is smaller, the epidemic will slow quickly, and as much as it is lower, the more manageable the situation is in real time, and cases are more isolated. And we will try to use this parameter to delineate in the abiogenesis and transmission only having the counts of the planets. Advantage of this number is actually that it follows dynamics within small portions of the space regions. Let us consider firstly experiment without knowledge of the individual original of life. Okay, for estimating effective reproduction number, there is no unique way. And here we will rely on this simple definition of this number as being proportional to infected entities. Also, we will rely to the Poisson process, the fact that has property to count points in any subset of the carrier space. And this count will have the Poisson distribution. So actually for any subset in larger space, the probability for having 0, 1, 2, etc. points in that subset is following Poisson distribution as well. And the parameter will be Poisson. And we will here actually consider the special case of Poisson distribution with variance mu and the natural parameter theta. We then accounting that actually Poisson process is probability density function, and we could relate counts of Poisson process with infected entities. And we can plot on this right the region containing R values larger than 1 in phase space defined by counts of planets with life versus total sample counts on y-axis. It is evident that we have polygon of complex shape with large number of vertices, and it can produce really optimistic ranges. For example, for sample with 2 planets, that is the lower vertex, we will have actually possibility, for example, for sample of 5 planets and observing 2 planets with life, that is the lower vertex, it will be indication of possible life transmission. For sample of about 20 planets, we will observe between 2 and 20 actually lower and upper bounds as a range for possible life transmission. For samples larger than 25, the lower and upper bounds are actually increasing simultaneously. Count data are notoriously hard to model. Not only do they not follow the normal distribution, but it is also possible that we have a larger dispersion of counts in the experiment than it is expected in Poisson distributions. And we can actually observe that our counts has larger variance than Poisson distribution. And then we will say that our data are over dispersed. And conversely, if the variance of our data are smaller than expected Poisson parameter, we will say that our data are under dispersed. Over or under dispersion is often caused by characteristics of the data that we cannot take into account on the site of experiment. However, we could take statistically into account over or under dispersion of counting of life-bearing planets by employing general Poisson process, where parameter A is a parameter determining over dispersion if it is larger than 1, or under dispersion if it is smaller than 1. And we use the same principle as in this case to plot the region of counts. So for example, to plot the region of parameter R with respect to the counts of exoplanets with life and the sample. And what we can see is actually here the lower triangle corresponding to the case of the over dispersion. And we can see that if we have the counts of planets with life about 20, it would be okay to say that R parameter is larger than 1 for samples containing 40 to 60 planets. However, for larger sample, we will have lower implication of a possibility of life transmission. Due to over-dispersion, contribution of larger counts above 60 will be somewhat lower. Similar situation will be for under-dispersed counts of exoplanets with life. And we can see here that 20 planets will have possibility to help us for the samples with a range about 20 almost to 90 objects. What we know that there are statistical tests which could measure under or oversampling of observed data. Next, we note that the value of parameter R can vary for a known rate with respect to time instances when life emerged on the planet. And if we could infer somehow that timeline of exoplanets and their life emergence, we could update our beliefs about the true value of parameter R based on the Bayesian rule. And the key insight here is given by Battencourt and Ribeiro in 2008, that actually we could relate the Poisson process and actually pandemic diffusion parameter R. What we are actually doing, we can formulate the likelihood function in the form of the Poisson process and parameterize it by this function. And then fixing the number of counted planets, we can vary the parameter R, and then we can see what we can get. Let us see what will happen if we face situation in this left column, something similar we simulated as in our solar system. We have, I hope that you can see, we have detected one planet with the life, and we have 4 time instances, timeline with 4, 5, 6, and 7 billion years. And what we get is actually, we produced here, you can see the likelihood of the parameter R given counts of the planet with life. And what we can see is actually that it is almost 0. And what we can then get from this, actually get our posterior belief about the parameter R, which is actually 0. And it means there is no transmission. That is actually just abiogenesis. We can also get closer look into this finding result if we construct the higher density interval, which summarize the distribution by specifying the interval that spans most of the possible distributions of parameter R, and that is about 95%. And we can see that HDI is very large, encompassing the R values larger than 1. So here we can see that we cannot say anything about, of course, transmission. Also, we tried to have, for example, 10 exoplanets with the same time of the life emergence. And what we got from that experiment is actually that the most likely parameter R is 0. It means that if we detect a larger number of exoplanets with almost the same time of life emergence, we will be more sure about abiogenesis. And in this following example on the right, we detected 10 exoplanets. On each we detected life in actually for the time span on 4, 5, 6, 7 to 13 billion years. Upper figure shows that for all time instances, there is one likelihood of parameter R given the count. However, when we construct the posteriors, what we can see that posteriors start without much confidence. They are all wide. We do not have good information, and progressively they became narrower, actually more confident about one value of the parameter R. Closer look into high density interval, that is this bottom plot, reveals that our parameter R over timeline converges to the value of 1, which is the boundary between the transmission and abiogenesis. And we can also see that our HDI is somewhat lower, between 0 and 2. And once again, we can see that with this sample, we actually not sure is it transmission or abiogenesis. And at the end, what I would like to say at the end, it is actually important. We presented 2 types of early experiments relating to the pure counting of exoplanets with the possible life. The first prototype is actually without any knowledge about any timeline of life emergence, while the second included it into itself. And it is important to emphasize that this all is still at a very early stage, and that we are looking forward to get input from the community. And if you have ideas and if you would like to contribute to the Life Space mission, we value your opinion. And please contact us, Daniel Angerhausen, or even me. And actually, you are also welcome to visit us. And at the end, once again, we would like to thank to all of you for your attention, and our special thanks goes to the NORCEL founder, Professor Zohan Gita, NORCEL director, Professor Martin Dominic, NORCEL manager, Lady Katie McGrath, and of course, special credits and thanks to Life Mission and Daniel Angerhausen, the lead of the project office. You are welcome to visit us, to communicate with us, and we are looking for your feedback. Thank you so much.